Have you ever stopped to think why Mars, the most studied planet after Earth, the destination of dozens of space missions, the focus of billions of dollars in scientific research, and humanity's dream of colonization, remains an almost impenetrable mystery to us? Neil deGrasse Tyson, one of the most respected astrophysicists in the world, recently made a statement that shook the scientific community and will make you rethink everything you thought you knew about the red planet. He revealed that the more we study Mars, the further our real understanding of that alien world becomes, and that we may never truly understand it in the way we imagine. This may sound contradictory, after all. We have rovers exploring its surface right now, probes orbiting around it constantly, decades of telescopic observations, and mountains of scientific data. So how is it possible that a planet so close and so studied remains fundamentally incomprehensible? The answer goes far beyond what you might think and has profound implications not just for Mars, but for our entire quest to understand alien worlds, and even for the possibility of finding life beyond Earth. Tyson explained that each new discovery about Mars, rather than completing the puzzle, adds pieces that don't fit any model we previously had, as if the planet is constantly showing us that our terrestrial categories of understanding simply don't apply to it. Think about it for a moment. We sent the first successful flyby to Mars in 1965 with Mariner 4, almost 60 years ago. And since then, we have accumulated more information about Mars than about any other celestial body besides Earth. But today, in 2025, leading scientists openly admit that we are more confused about fundamental aspects of that planet than we were decades ago. How is this possible? How can knowledge generate more questions than answers? And if you are one of those who love unraveling the mysteries of the cosmos like me, subscribe to the channel because we have many more fascinating scientific revelations to share with you, and this story about Mars will challenge everything you thought about how science works and the limits of human knowledge. Let's start with the most basic and surprising. Mars is just 55 million kilometers away from Earth at its closest approach, which in cosmic terms is practically our immediate neighborhood, a planet we've been able to observe with the naked eye for as long as humans have been looking at the night sky, and ancient civilizations have been mapping its movements with impressive precision for thousands of years. The Babylonians recorded the position of Mars 4,000 years ago. The ancient Egyptians called it Har-Dasher, or the Red One, and virtually every human culture that has looked at the stars has given special names and meanings to that red light that moves differently than the fixed stars. For centuries, Mars has fueled our imagination in ways that no other planet has been able to do so. At the end of the 19th century, astronomers such as Giovanni Schiaparelli and Percival Lowell observed through telescopes what they interpreted as canali on the Martian surface, an Italian word meaning canals, but which was erroneously translated into English as canals, implying artificial structures. This simple linguistic confusion triggered decades of speculation about an advanced Martian civilization that built an elaborate network of canals to transport water from the poles to equatorial regions as the planet dried. Percival Lowell dedicated years of his life, his personal fortune, and even built an entire observatory in Arizona specifically to study Mars, and map these supposed waterways, producing detailed maps and devising theories about a dying civilization fighting for survival in a desertified world. Herbert George Wells, inspired by these ideas, wrote The War of the Worlds in 1898, imagining desperate Martians invading Earth in search of resources that their planet could no longer provide. Edgar Rice Burroughs created a whole series of novels about Barsoom, the Mars of his imagination, with alien princesses and conflicting civilizations beneath the planet's two satellites. Mars became the definitive symbol of alien life in popular culture. And this fascination wasn't just fiction, It was backed up by what the best scientists of the time genuinely believed they were observing. But here begins the first layer of the fundamental misunderstanding about Mars that Neil deGrasse Tyson points out. We project our earthly expectations onto that alien world before we even have real data about it. When the first space missions finally reached Mars in the 1960s, the revelation was devastating for those who dreamed of Martian civilizations. NASA's Mariner 4 made the first successful flyby in July 1965 and transmitted 22 grainy, blurry images of the Martian surface. But even at that low resolution, the truth was undeniable. Mars appeared dead, covered in craters like the Moon, with no obvious signs of vegetation, canals, or any structure that might suggest intelligent life. It was a cultural and scientific shock. The images showed a rocky and desolate desert, frozen and hostile, with an atmosphere so thin that it was practically non-existent compared to terrestrial standards. Lowell's elaborate canals? They didn't exist. The seasonal changes that supposedly indicated vegetation growing and dying? Global dust storms were revealed that periodically changed the appearance of the planet. Mars, apparently, was just a dead rock in space, interesting geologically, but with nothing approaching the dramatic narrative we had constructed for centuries. And it was precisely at this moment that the real misunderstanding about Mars began to solidify, because we responded to that disappointment by creating a new, simplified mental model. Mars, the dead, barren planet. A world that lost its atmosphere billions of years ago, dried out completely and became a larger, more interesting version of our Moon. This model would dominate scientific and popular thinking for decades to come, and it is precisely this oversimplification that Neil deGrasse Tyson is warning us against now. NASA's Viking missions that landed on the Martian surface in 1976 seemed to confirm this view of Mars as a barren, dead desert. The two Viking landers performed the first sophisticated experiments to detect microbial life in Martian soil, but the results have been ambiguous and controversial at best to this day. Most scientists interpreted the data as negative, concluding that Mars was chemically and biologically inert, just a cold rock in space, with nothing especially interesting going on in terms of active processes. The images sent by the Vikings showed deserted landscapes, rocks scattered across reddish plains, without movement, without changes, without anything happening. This static, dead Mars became the scientific consensus, and with it came a certain complacency. We thought we understood Mars. It was simply a planet that had been lost. It was a geological record frozen in time of processes that occurred billions of years ago, a dead archive of the solar system's past. But then, something extraordinary started to happen as our technologies improved, and we were able to study Mars with increasingly sophisticated instruments. The Mars Global Surveyor, launched in 1996, began mapping Mars in unprecedented detail, using ground-penetrating radar and high-resolution cameras. And the images that came back made no sense within the dead static model of Mars we had built. There was clear and unambiguous evidence that liquid water had flowed on the Martian surface in the relatively recent past, not just billions of years ago, but perhaps as recently as millions or even thousands of years ago. Drainage valleys that seemed to be carved by rivers, deltas of ancient lakes, geological formations that on Earth only form in the presence of running water. All of this was present on Mars, but the current planet did not have liquid water on the surface. The atmospheric pressure was too low for that. The water would simply sublime straight from ice to vapor without going through the liquid state. How could these formations be so recent? The model did not close. And then came the discovery that really shook everything up. Evidence that water still flows seasonally on Mars today. In 2015, scientists announced that they had detected dark lines on the slopes of Martian craters that appear during the warmest months of the Martian year and disappear during the winter. And spectroscopic analysis strongly suggested the presence of hydrated salts, that is, salty water flowing across the Martian surface right now, at this very moment, under atmospheric conditions that theoretically should make this impossible. Neil deGrasse Tyson pointed out in one of his talks that every time we think we finally understand Mars, that we have created a consistent model that explains all the observations, the planet throws a new piece on the table that breaks the entire previous model. We're not just dealing with gaps in knowledge that we can fill with more data. We're dealing with a world that appears to operate on principles we don't yet fully understand. And this discovery impacts our scientists around the world. And I wonder, where are you watching from now? Comment your city or country. It's incredible to think that we are all connected in this same universe, trying to understand it better. Looking at the same night sky, where Mars shines and challenges us to understand it. The Martian atmosphere is another perfect example of this fundamental misunderstanding that Tyson highlights. We know that Mars has just 1/100th the atmospheric pressure of Earth at sea level, a tenuous atmosphere composed mostly of carbon dioxide with traces of nitrogen and argon. This atmosphere is so thin that it should be incapable of sustaining complex meteorological processes, but Mars has dust storms that can cover the entire planet, winds that shape immense dunes, clouds that form and dissipate, and even carbon dioxide snow that falls from the polar skies. How can such a rarefied atmosphere generate such dramatic meteorological phenomena? The physics involved are not yet completely understood, and it doesn't stop there. Recent measurements have shown that Mars is losing its atmosphere to space right now at a much faster rate than models predicted, stripped away by the solar wind because the planet doesn't have a strong global magnetic field to protect it. But if it's losing atmosphere so quickly now, how has it managed to maintain any atmosphere for billions of years? Where does the replacement come from? Is there active volcanism that we have not detected? Are gases released from the interior through processes that we are not aware of? Or are our atmospheric loss models fundamentally wrong? The Mars Reconnaissance Orbiter detected in 2008 that avalanches occur on the polar cliffs of Mars, giant blocks of carbon dioxide ice collapsing down the slope, creating clouds of dust and fragments. A dynamic and active process happening now, not billions of years ago. The Curiosity rover, which landed in Gale Crater in 2012, made a discovery that left scientists completely baffled. Regular seasonal variations in methane levels in the Martian atmosphere. Methane is an organic molecule that on Earth is strongly associated with life, although it can also be produced by geological processes. But on Mars, methane levels rise and fall cyclically with the Martian seasons, increasing in late northern hemisphere summer and decreasing in winter, suggesting an active and continuous source releasing methane and some process periodically removing or consuming that methane. No one knows for sure where this methane comes from or where it goes. Could it be microbial life underground releasing methane as metabolic waste? Could it be a chemical reaction between rocks and heated groundwater that abiotically generates methane? Why are variations seasonal and not constant? Scientists have proposed dozens of hypotheses, each with problems and gaps, and the more we study Martian methane, the less certain we are about its origin. Tyson has used this exact methane example on several occasions to illustrate why Mars is so misunderstood. Because every answer we find generates 3 new questions, and the questions become more fundamental and challenging, not simpler and more technical. We're not just filling in details into a picture we already understand. We're discovering that the entire picture we built was wrong from the start. The Perseverance rover, which arrived on Mars in February 2021, is exploring an ancient crater lake called Jezero, where orbital evidence strongly suggested the presence of water-formed sedimentary deposits, the perfect kind of place to look for signs of ancient life preserved in rocks. But when Perseverance began analyzing the rocks at the bottom of the crater, it discovered that many of them are igneous rocks, formed by volcanic processes, not sedimentary rocks formed by deposition in water as we expected. How is this possible? The crater clearly appears to have been a lake from the orbital images. There is a river delta preserved on the edges, where water flowed into the crater. So why is the bottom covered in volcanic rocks? The most likely answer is that the geological history of Mars is much more complex and chaotic than we imagined, with multiple phases of volcanic activity, catastrophic floods, drying out, more volcanism, possibly more water, all occurring in sequences that we have not yet been able to adequately reconstruct. Each site we study in detail reveals a more complicated story than we expected. And when we try to integrate all of these sites into a coherent narrative of Mars's evolution, the pieces simply don't fit together perfectly. Neil deGrasse Tyson argues that part of the fundamental problem is epistemological, having to do with the very nature of how we acquire knowledge about Mars. We are trying to reconstruct the 4.5 billion-year history of an entire planet from data collected at a few dozen specific locations over a few years or decades of observation. Imagine trying to understand the entire history of the Earth, its geology, climate, biology, and evolution, by studying just a few rocks in 3 or 4 different deserts for 10 years, and never being able to visit oceans, forests, mountains, volcanoes, or polar ice caps directly. How complete would your understanding be? How confident would you be in your conclusions? This is exactly the situation we are in with Mars. We have an incredibly biased and limited sample of an entire world, and we are trying to extrapolate general principles from this tiny sample. And here is the even deeper problem that Tyson emphasizes. Mars is not just a different version of Earth. It is not a direct analog where we can apply our terrestrial understanding with small adjustments. Mars is a completely different type of world operating in a planetary configuration that we have no close analog to study. It is a planet too small to maintain active plate tectonics like Earth, but too large to have completely cooled like the Moon. It has much lower gravity than Earth, which profoundly affects how atmosphere, water, and even rocks behave. It has had abundant liquid water on its surface for significant periods in the past, but has never developed a complex global hydrological cycle like Earth's. It may have had life, but if it did, that life evolved under conditions completely different from those on Earth, and may have used different biochemistry. We're trying to understand something fundamentally alien using categories and models developed to understand Earth, and it just doesn't work properly. The question of Mars's magnetic field is particularly revealing of this fundamental misunderstanding. Earth has a strong global magnetic field generated by the movement of liquid iron in its outer core, a planetary dynamo that protects our atmosphere from the solar wind and gives us the beautiful aurora borealis. Mars has no significant global magnetic field today, but orbiting probes have detected specific regions of the Martian crust that are intensely magnetized, especially in the planet's southern hemisphere. These regions show that Mars had a strong global magnetic field at some point in the distant past, generated by a dynamo in its core when the planet was young and its interior was still hot and convective. But then, at some point, approximately 4 billion years ago, the Martian dynamo simply stopped, the magnetic field collapsed, and the solar wind began to slowly strip away the Martian atmosphere. Why did the dynamo stop? The standard explanation is that Mars's core cooled enough for the iron to solidify or stop convecting properly, but new seismic measurements by the InSight probe, which operated on Mars from 2018 until 2022, have revealed that Mars's core is surprisingly large and probably still liquid, much larger than models predicted. If the core is still liquid, why is there no dynamo? Why is there no magnetic field? We are clearly missing something fundamental about how planetary dynamos work. And this has huge implications not just for understanding Mars, but for understanding how rocky planets evolve in general, including planets in other solar systems that we are beginning to detect and characterize. InSight also detected something completely unexpected. Mars has earthquakes, or rather Marsquakes, continuous seismic activity indicating that the planet's interior is still active and dynamic. Some of these Marsquakes are small and shallow, probably caused by thermal contraction of the crust as the planet cools, or by adjustments in the crust carried by large volcanoes. But others are deeper and stronger, originating in the Martian mantle and suggesting processes of convection or magma movement that we would not expect to find on a dead planet. InSight recorded more than 1,300 Marsquakes during its mission, revealing that Mars is much more seismically active than the Moon, although less active than Earth. Why does a planet that should theoretically have cooled and become geologically dead still exhibit so much internal activity? Is there active volcanism that we haven't detected on the surface because it's occurring on timescales too long for us to observe directly? Is the Mount Olympus volcano, the largest mountain in the solar system with a height of 21 kilometers and a base 400 kilometers in diameter, truly extinct or merely dormant, waiting tens or hundreds of millions of years between eruptions? We don't know. Every instrument we send to Mars reveals active processes that contradict the idea. They act from a dead and static planet, but we do not have a unified theory that explains all these processes adequately. Neil deGrasse Tyson compared this situation to the history of physics in the early 20th century, when phenomena such as the photoelectric effect and black-body radiation contradicted well-established classical physics, and these contradictions eventually led to the development of quantum mechanics, a complete revolution in our understanding of the fundamental nature of reality. He suggests that we may be in an analogous situation with Mars, where our current theories of planetary evolution are fundamentally inadequate, and we need a new conceptual framework, a new paradigm for understanding how intermediate planets like Mars evolve and function. But developing this new paradigm requires much more data than we currently have. Data that we will only obtain with more ambitious missions, including eventually manned missions that can explore the planet with the versatility and intuition that only humans bring to scientific exploration. The question of possible life on Mars is where this fundamental misunderstanding becomes most critical and most frustrating. The Viking experiments in the 1970s were designed based on assumptions about how microbial life should behave, assumptions derived entirely from our experience with terrestrial life. When results were ambiguous and didn't quite fit expectations, the standard interpretation was that they were false positives caused by unusual inorganic chemistry in Martian soil. But what if the experiments detected life, but a form of life so different from Earth's that we don't recognize the signs properly? What if Martian life, if it exists, uses biochemistry based on perchlorates, molecules that abound in Martian soil and that would destroy the organic compounds that the Viking experiments were looking for? Decades later, there are still scientists arguing that the Viking data is consistent with microbial life if we abandon our earthly assumptions about how life must work. The problem is that we don't know how to look for life we don't know about. We don't have a universal definition of life that applies beyond terrestrial examples. And that means we could be looking directly at evidence of Martian life and not recognize it because it doesn't look like what we expect. The Perseverance rover is currently collecting samples of Martian rocks that will be left on the surface for eventual collection by a future sample return mission, a mission that will bring rocks from Mars to terrestrial laboratories where we can analyze them with much more sophisticated instruments than we have been able to send to Mars. This sample return mission, called Mars Sample Return, is seen by most planetary scientists as essential to truly advancing our understanding of Mars, Because no matter how good the rovers and probes we send, they carry limited instruments operating under difficult conditions and cannot do the kind of detailed, multifaceted analysis that terrestrial laboratories allow. But even if we bring Martian rocks to Earth and analyze them thoroughly, we will be interpreting those rocks through the lens of our earthly understanding of geology, geochemistry, and possible biology. If Mars has geological processes that do not exist on Earth, if it had environmental conditions that never occurred here, if life developed with alternative biochemistry, our interpretations will still be limited by the boundaries of our experience and imagination. Tyson argues that we may never fully understand Mars until humans are living there permanently, exploring extensively, developing a Martian intuition through prolonged direct experience, in the same way that terrestrial geologists have developed intuition about the Earth through centuries of fieldwork. Only when we have scientists walking the Martian surface, selecting rocks with human judgment, following hunches based on subtle observations, conducting impromptu experiments in response to unexpected discoveries, only then will we begin to develop the kind of intimate, deep understanding we have of Earth. And even that may not be enough, because Mars is fundamentally an alien world that may require decades or centuries of intensive study before we truly understand it. There is also a deeper philosophical question embedded in this discussion about understanding Mars, a question about the limits of scientific knowledge when applied to unique historical systems. Science works best when it can do repeated experiments, isolate variables, test hypotheses under controlled conditions, and build predictive models that work consistently. But Mars is a single sample, a single experiment, the natural planetary evolution that happened over billions of years under conditions that we can never replicate or control. We can't go back in time and watch Mars lose its atmosphere and water. We can't vary conditions and see what happens. We can't compare with multiple examples of similar planets evolving in different ways. We have only one Mars, with a specific and unique history, and we are trying to reconstruct that history like cosmic archaeologists working with fragmentary and incomplete evidence. Neil deGrasse Tyson often makes an analogy. Imagine you've never seen a completed film, but someone shows you 5 random frames from a 2-hour film and asks you to reconstruct the entire plot, characters, theme, and ending. You could make some inferences, create some theories, but how confident would you be in your conclusions? How complete would your understanding of the film be? That's essentially what we're trying to do with Mars, reconstruct 4.5 billion years of complex planetary history from limited snapshots in the present and a few fragmentary glimpses of the past preserved in geological formations. The task is almost impossible in its ambition, and it is perhaps presumptuous to expect that we will be able to fully understand Mars in the coming decades or even centuries. But that doesn't mean we should give up, or that the effort is futile, because the very process of trying to understand Mars is teaching us profound things about planets, atmospheres, geology, possible abiogenesis, and the limits of our own ability to understand. And if these discoveries blew your mind as much as mine, leave a like, subscribe to the channel, and turn on notifications because we have many more mysteries of the universe to unravel together. And believe me, this journey is just beginning. There's one particularly intriguing aspect of the misunderstanding of Mars that Tyson highlighted in a recent interview and that rarely gets the attention it deserves: the issue of the 2 Martian satellites, Phobos and Deimos. These 2 small, irregular moons orbit very close to Mars, especially Phobos, which is just 6,000 kilometers above the Martian surface, and orbits the planet in just 7 hours and 39 minutes, faster than Mars rotates on its own axis, meaning that Phobos rises in the west and sets in the east as seen from the Martian surface, the opposite of all other celestial objects. For decades, we assumed that Phobos and Deimos were captured asteroids, rocks that roamed the solar system and were captured by Mars's gravity at some point in the distant past. This explanation seemed to make sense because both moons have asteroid-like appearance, similar composition to C-type asteroids found in the asteroid belt, and orbits very close to the equatorial plane of Mars. But there is a huge problem with this theory that has only recently begun to be widely recognized. Capturing asteroids in such close circular orbits is extremely difficult, almost impossible, given Mars' relatively weak gravitational field and the absence of a dense atmosphere that could have slowed the asteroids down through atmospheric friction during capture. Computer simulations show that the probability of Mars capturing not one but two asteroids in nearly circular orbits in the equatorial plane is incredibly low. And even if it did manage to capture an asteroid, that asteroid would likely be in a highly elliptical and inclined orbit, not the nearly perfectly circular orbits we observe. So if they're not captured asteroids, where did Phobos and Deimos come from? The alternative theory gaining traction is that they formed from debris from a gigantic impact on Mars billions of years ago, similar to how our own moon likely formed from debris when a Mars-sized object collided with the forming proto-Earth. But if Phobos and Deimos are the products of a giant impact, that has huge implications for the early history of Mars that weren't in our previous models. An impact large enough to create these moons would have heated the Martian surface tremendously, possibly vaporizing entire oceans if they existed at the time, ejecting enormous amounts of atmosphere into space and fundamentally altering the young planet's geology and climate. Did this happen before or after Mars had abundant liquid water? How many giant impacts did Mars experience in its youth? How did this affect the potential for life to develop? We don't know, and every answer we find to the origin of Phobos and Deimos opens a cascade of new questions about the early history of the solar system and the evolution of all the rocky planets. And there's more. Phobos is gradually approaching Mars due to tidal effects, and calculations show that in approximately 50 million years, Phobos will cross the Roche limit and be destroyed by Mars' differential gravity, breaking into pieces that will form a temporary ring around the planet before eventually falling to the surface as a spectacular meteor shower over millions of years. This means that we are living in a special time in the history of Mars, a time when the planet has two moons, but is about, in geological terms, to destroy one of them spectacularly. Is this coincidence, or is there something about our moment in time that we don't understand? Questions like this sound like philosophy, but they have real scientific implications about observational sampling and probabilistic inference in the cosmological context. The history of water on Mars is probably the most confusing and misunderstood aspect of the entire planet. And this is where Neil deGrasse Tyson's observations about fundamental misunderstanding really shine. We have overwhelming geological evidence that Mars had abundant liquid water on its surface 3 to 4 billion years ago during the period called the Noachian. Huge drainage valleys, craters that clearly were lakes, minerals that only form in the presence of abundant liquid water, layered sedimentary formations that indicate deposition in aquatic environments, all point to a young Mars that was wet and possibly even had oceans covering large portions of the northern hemisphere. Some scientists estimate that Mars may have had enough water to cover the entire planet, with an oceanic layer 150 meters deep, or concentrated in real oceans in the northern hemisphere, with depths of up to 1.5 kilometers. This wet Mars could have had rain, clouds, snow, seasonal freeze-thaw cycles, perhaps even life swimming in its primordial seas. But then, at some point approximately 3.5 billion years ago, something dramatic happened, and Mars lost most of its atmosphere and all of its liquid surface water, transforming into the frozen desert we see today. What happened? The standard narrative is that Mars' magnetic field collapsed first, leaving the atmosphere unprotected against the solar wind, which then began ripping off atmospheric atoms and carrying them into space. And as the atmosphere shrank, the pressure and temperature dropped to the point where liquid water could no longer exist on the surface, forcing all the water to freeze or sublimate, and the planet dried up. This narrative is plausible and widely accepted, but the more we examine it, the more problems appear. First, the rate of atmospheric loss we measure today is too low to explain the loss of a dense atmosphere in just a few 100 million years, even taking into account that the loss was probably faster in the past, when the young sun had a more intense solar wind. Second, if Mars lost its water 3.5 billion years ago, why do we see geological evidence of liquid water flowing on the surface at much more recent times, just hundreds of millions or even millions of years ago? There are formations that clearly appear to have been carved by flowing water on geologically recent timescales, long after the planet supposedly dried out completely. This suggests that Mars went through multiple phases of wet and dry climate, possibly due to extreme variations in the planet's obliquity, the angle between its axis of rotation and the plane of its orbit. The Earth's obliquity is stabilized by the Moon, remaining between 22 and 25 degrees over millions of years, which gives our planet relatively stable climates. Mars does not have a large stabilizing moon, and calculations show that its obliquity may have varied chaotically between 0 and 60 degrees throughout its history, causing extreme climate changes. When the obliquity is high, the poles receive more direct sunlight during the summer. Carbon dioxide polar ice sublimates in large quantities, releasing additional atmospheric pressure. The atmosphere temporarily thickens, and the temperature rises enough to melt water ice at mid and high latitudes, creating short periods of warmer, wetter weather before the obliquity changes again and everything freezes again. This hypothesis would explain evidence of recent aquatic activity, but it raises its own questions. How much water is still trapped in the Martian subsurface and polar ice caps? Could Mars experience episodes of temperate weather again in the distant future? If there have been repeated periods of habitable conditions throughout Martian history, does this increase or decrease the likelihood that life arose and survived? We do not have definitive answers to any of these questions. Then there is the question of the possible ancient Martian ocean, called Oceanus Borealis, which theoretically covered the landslows in the northern hemisphere of Mars billions of years ago. Radar images showed what appeared to be ancient shorelines around the northern plains, suggesting that there was contact between water and land at consistent elevations, exactly what you would expect to see if there was an ocean. But when scientists examined these supposed coastlines in detail, they discovered that they are not perfectly level as they should be if they were actually formed by a stable ocean. There are variations of up to 1 kilometer in altitude at different points along the supposed lines, far more than could be explained by later tectonic or volcanic activity. How could an ocean leave such irregular shorelines? One possibility is that the ocean was never stable, existing only briefly during episodes of extreme climate warming when huge amounts of ice melted catastrophically, creating temporary oceans that lasted perhaps only thousands or tens of thousands of years before freezing or sublimating again. Another possibility is that our understanding of how coastlines form and preserve themselves is wrong, based too much on terrestrial experience, where plate tectonics and erosion shape landscapes in ways that do not occur on Mars. Or perhaps the lines we think are coastal actually represent something completely different, some Martian geological process that has no terrestrial analog and that we have only just begun to imagine. And here's an even deeper mystery that leaves many scientists perplexed. If Mars had oceans and rivers billions of years ago, where is all the sedimentation? On Earth, billions of years of water erosion have created miles of layered sedimentary rocks, deposits of clay, sandstone, limestone, all products of eroded material being transported by water and deposited in basins, oceans, and deltas. Mars should have similar, vast layers of sediment filling the low-lying basins of the northern hemisphere if there really was an ocean there. But when the Mars Reconnaissance Orbiter's penetrating radar examined the subsurface of these regions, it found much less sedimentation than we expected, and much of what is there appears to be volcanic rock, not sedimentary. Where did all the sediment that should have been generated by billions of years of water erosion go? Were they covered by later lava flows? Were they eroded again and transported elsewhere? Are they buried deeper than our radars can penetrate? Or did Mars simply have much less aquatic erosion than we think, and the rivers and oceans were much more brief and spasmodic phenomena than we imagined? Each of these possibilities has radically different implications for the habitability of Mars and the possibility that life arose there. A Mars with stable oceans lasting hundreds of millions of years is a much more promising environment for abiogenesis than a Mars with ephemeral oceans that appear and disappear in short-lived catastrophic episodes. But we can't definitively distinguish between these scenarios with the data we have. Neil deGrasse Tyson mentioned in an interview that this uncertainty about something as fundamental as whether or not Mars had long-lasting oceans is embarrassing for planetary science, but it is also honest, and recognizing this misunderstanding is the essential first step to eventually developing real understanding. Scientists are sometimes tempted to present excessive confidence in their theories to the public because they assume that admitting uncertainty will be interpreted as weakness or ignorance. But Tyson argues that it is exactly the opposite. Admitting what we do not know is a demonstration of intellectual strength and scientific rigor, and the public can and should understand that science is a process of continuous refinement of understanding, not a set of fixed and unchanging truths. Another truly perplexing aspect of Mars that defies understanding is the crustal dichotomy. The bizarre fact that the planet's southern hemisphere is predominantly ancient, densely cratered highlands, while the northern hemisphere is mostly smooth, low plains with far fewer craters. This abrupt division between the two hemispheres is unparalleled on any other rocky planet we know of. Earth has nothing like it. Our topography is dominated by plate tectonics that creates complex patterns of continents, mountain ranges, and ocean basins with no clear hemispheric division. The Moon and Mercury have some hemispheric variation, but nothing as dramatic as Mars, where the average difference in elevation between north and south is about 3.5 kilometers. How did this happen? The most popular hypothesis today is that Mars was hit by an absolutely immense object in the first million years of its existence, a giant protoplanet or asteroid that collided with the hemisphere. Or north with enough force to literally rip away miles of crust and create the Borealis Basin, an impact structure that would cover 40% of the planet's surface, by far the largest known impact crater in the solar system. This impact would have been so catastrophic that it would melt much of the Martian mantle, create temporary oceans of lava covering the northern hemisphere, possibly eject so much material into space that it would form the satellites Phobos and Deimos and fundamentally alter the geological and climatic evolution of Mars forever. But this mega-impact theory, dramatic as it is, has problems. An impact of this magnitude should have created a circular raised rim around the basin, as we see in all other large impact craters, but the transition between the southern highlands and northern lowlands on Mars is gradual in many places, not abrupt like a crater rim. Additionally, we should see evidence of impact ejecta spread across the entire southern hemisphere. But the distribution of rock types is not consistent with this. Alternative theories have been proposed, including the possibility that the dichotomy was created by internal convection processes in the Martian mantle that concentrated volcanic activity in the northern hemisphere, or that it was the result of a very ancient form of primitive plate tectonics that operated briefly when Mars was young before stopping when the planet cooled too much. But each of these theories has its own inconsistencies with observations, and the truth is that we don't really know how the crustal dichotomy formed. It is possible that multiple processes contributed: giant impact plus extensive volcanism plus early crustal differentiation, all working together in ways we have not yet been able to adequately model. Tyson used the crustal dichotomy as a perfect example of how Mars defies categorization, because we are trying to fit it into models designed to understand Earth, Venus, Mercury, and the Moon. But Mars just doesn't fit neatly into any of those categories. It's something different, an in-between type of planet, with its own unique physics and history that we don't yet adequately understand. The possibility of current life on Mars, not just ancient life preserved in rocks, but microbial life still existing today in protected niches, is perhaps the most important and most misunderstood question about the planet. For decades after the Viking missions, the scientific consensus was that Mars was barren, completely devoid of life due to intense ultraviolet radiation on the surface, extremely low temperatures, tenuous atmosphere, and the presence of perchlorates in the soil that are toxic to life as we know it. But that consensus has begun to fragment as we discover extreme terrestrial environments where life thrives in conditions that we once thought were absolutely impossible for biology. Microbes living in rocks several kilometers below the Earth's surface, where there is no sunlight, liquid water is scarce, and temperatures are very high. Bacteria surviving in hyperalkaline or hyperacid lakes that would dissolve human flesh in minutes. Organisms growing in salt-saturated evaporates where water activity is so low that DNA should be irreversibly damaged. Microbes that use arsenic in place of phosphorus in their biological molecules. Life basing its energy on chemical reactions between rocks and water in the complete absence of sunlight. Entire ecosystems existing independently of photosynthesis. Each of these discoveries has expanded our understanding of the limits of life and simultaneously expanded the environments on Mars that we consider potentially habitable. If terrestrial microbes can survive several kilometers below the surface, where they never see sunlight, why couldn't there be Martian microbes living deep underground, where there is still liquid water, protected from surface radiation, extracting energy from chemical reactions between water and minerals? If terrestrial extremophiles tolerate perchlorates and even use them metabolically in some cases, why couldn't Martian life have evolved perchlorate-based biochemistry from the beginning? If life on Earth began nearly 4 billion years ago when our planet was young and hostile, why couldn't life have begun on Mars during the same period when Mars had potentially more favorable conditions than it does today? And if life arose on Mars, then, where would it be now? Completely extinct? Or taking refuge deep underground, persisting in protected environments that we have not yet explored? These are not rhetorical questions. They are legitimate scientific questions that we can only answer with future missions specifically designed to look for signatures of current life, not just ancient fossilized life. The challenge is that looking for current life on Mars requires drilling deep underground, perhaps hundreds of meters or even kilometers below the surface, because it is unlikely that life could survive in today's hostile surface conditions. No current mission has the capacity to drill this deeply. Current rovers can drill just a few centimeters into surface rocks for analysis, completely inadequate for accessing possible underground biospheres. So we are in a frustrating situation where we suspect that if there is life on Mars today, it is beyond our current reach, and we won't know if it exists until we develop much more advanced drilling technology and bring it to Mars, something that probably won't happen until manned missions establish a permanent presence, allowing large-scale drilling operations. Do you think it's worth continuing to invest billions in Martian exploration with no guarantee of discovering life? Or should we focus on other worlds like the moons of Jupiter and Saturn that may have more accessible subsurface oceans? Comment your opinion. I really want to know what you think about priorities in the search for extraterrestrial life, because this issue affects how we spend limited resources on planetary science. Neil deGrasse Tyson made a particularly provocative observation about Mars and human colonization that many people in the space community found controversial, but which perfectly illustrates his point about how poorly we understand the planet. He argued that all the talk about colonizing Mars in the coming decades is premature and potentially dangerous, because we simply don't understand the planet well enough to plan for a permanent human presence responsibly. Think about the challenges. We need to know where accessible water is in sufficient quantities to support a colony, but our understanding of subsurface ice distribution is fragmented and incomplete. We need to understand the health risks of Martian dust, which is loaded with perchlorates and possibly other toxic oxidants, and has extremely fine particles that can penetrate deep into human lungs. But we have never tested prolonged exposure of human tissue to real Martian dust in Martian gravity. We need to know how the human body responds to the gravity of Mars, which is only 38% of Earth's, for periods of years or decades. But we have never done these experiments because we cannot simulate partial gravity in Earth orbit. For prolonged periods, we can only achieve microgravity or complete gravity, nothing in between. We need to understand the radiation environment on Mars, both at the surface and in the shallow subsurface where habitats could be built. But our measurements are limited and do not fully capture the spatial and temporal variation of radiation during solar storms and different points in the 11-year solar cycle. Tyson isn't saying we shouldn't colonize Mars eventually. He's saying the responsible sequence is, first, fully understand the planet through decades of advanced robotics and possibly near-term manned scientific missions. Second, develop life support and protection technologies specific to real Mars conditions, not theorized conditions. Third, only then consider permanent establishment of self-sustaining colonies. Jumping straight to colonization without full understanding is, in their view, putting human lives at unnecessary risk based on enthusiasm and technological optimism rather than sound scientific planning. And he has a valid point. The history of human exploration is replete with examples of expeditions that failed catastrophically because they underestimated the challenges of the environment they were entering into. From 19th-century Arctic expeditions to the first mountaineering attempts in the Himalayas, nature has repeatedly punished human arrogance and poor planning. Mars will be no different. It will be much more unforgiving and less forgiving of mistakes than any terrestrial environment. And we won't have rescue teams able to arrive in hours or days if something goes wrong. We will be on our own for months or years, depending on the launch windows between Earth and Mars. This does not mean that colonization is impossible or that we should not try. It means that we must proceed with scientific humility, explicitly acknowledging everything we do not know and working systematically to fill these gaps in knowledge before irrevocably compromising human lives. The space community, especially the private sector led by companies like SpaceX, sometimes demonstrates a confidence bordering on arrogance about our ability to overcome Martian challenges through engineering and determination, but Tyson reminds us that nature doesn't care about our determination. The physics of Mars will operate in exactly the same way. Form regardless of how motivated or technologically advanced we consider ourselves to be. Do you agree with this cautious approach, or do you think we should be bolder and accept more risks to move forward faster? It's a philosophical question as much as a technical one about how we balance progress and security, dreams and realism, ambition and humility. There is also a deep psychological and existential dimension to our relationship with Mars that contributes to the misunderstanding about the planet. Mars has held a special place in the human imagination for millennia, long before we had any technology to study it up close. Its blood-red color associated it with war and conflict in virtually every ancient culture. The Romans named it after their god of war. The Greeks called it Ares, also their god of war. Mesoamerican cultures had warrior deities associated with the planet. There was something universally unsettling about that moving red light in the night sky. But with the scientific era, Mars took on a different meaning. It became the symbol of the possibility of life beyond Earth, of the future of humanity as a multiplanetary species, of our cosmic destiny. We have projected so many hopes, fears, and fantasies onto Mars that it has become almost impossible to view it objectively as simply another planet with its own geology, climate, and history. When we think about Mars, we're not just thinking about a rocky body orbiting the Sun at an average distance of 228 million kilometers. We're thinking about all the stories we've told about it, from H.G. Wells's The War of the Worlds to Kim Stanley Robinson's Martian trilogy, from Lowell's Martian discoveries to Elon Musk's colonization plans. Mars carries immense symbolic weight in human culture, and this weight distorts our perception and understanding. Tyson points out that this emotional and cultural burden can actually get in the way of good science, because when scientists are unconsciously seeking to validate pre-existing narratives about Mars rather than simply following the data wherever it leads, they introduce subtle biases into interpretations, mission selection, and even into which questions they consider important enough to investigate. One example is the disproportionate obsession with searching for signs of life on Mars, compared to other equally important scientific goals, such as understanding the planet's climate evolution, its deep internal structure, or its interaction with the solar wind. I'm not saying that searching for life isn't important. It's absolutely crucial, but when it completely dominates the Martian agenda at the expense of other types of investigation, we miss opportunities to understand fundamental aspects of the planet that may eventually be essential even for interpreting any sign of life we find. If we discover Martian microbes, but do not understand Martian geochemistry deeply enough to determine whether these microbes are native or terrestrial contamination carried by our own ships, the discovery will be compromised and disputed indefinitely. We need a balanced Mars program that seeks life, but also builds fundamental understanding of the planet as an integrated system, and that requires resisting the temptation to focus myopically on only the sexiest, most culturally charged issues. It's difficult to maintain that balance when space agencies need to justify their budgets to politicians and the public who want dramatic headlines about alien life, not technical reports on mineral composition or crustal magnetic field variations. But good science requires patience, discipline, and a willingness to do the less glamorous fundamental work that eventually makes breakthrough discoveries possible. So where does this leave us? If Neil deGrasse Tyson is right, that Mars is fundamentally misunderstood, and may remain so for a long time, what is the way forward? How do we transform misunderstanding into understanding? The answer, according to Tyson and most planetary scientists, is a long-term commitment to systematic, multifaceted exploration of Mars, combining orbital missions, surface rovers, sample return missions, deep drilling missions, and eventually scientific human presence. There are no shortcuts. There is no single miraculous mission that will solve all the mysteries of Mars at once. The Mars Sample Return mission being planned by NASA and ESA to collect the samples that Perseverance is collecting and bring them to Earth is absolutely essential and should be a top priority, because ground-based laboratory analysis of real Martian rocks using the full range of modern analytical instruments will provide insights impossible to obtain with remote rovers. We need drilling missions that can access the deep subsurface of Mars, not, just a few centimeters, but meters or tens of meters, to sample buried ice, possible aquifers, and protected environments where current life could persist. We need a global seismic network on Mars, not just 1 or 2 stations, but dozens of them distributed across the entire planet, to map deep internal structure with the same resolution we have for Earth. We need missions that study Mars' upper atmosphere and its interaction with the solar wind in much greater detail than we have been able to do so far, to truly understand the mechanisms of atmospheric loss. We need more orbiters with advanced instruments that can map surface chemical and mineralogical composition globally, not just in selected locations. And eventually, we need humans on Mars, not as permanent colonists yet, but as field scientists doing the kind of versatile, responsive exploration that only humans can do, collecting samples with trained scientific judgment, following subtle clues, making contextual observations that programmed rovers simply cannot. Each of these missions individually won't answer every question about Mars, but collectively, over decades, they will build the kind of deep, multidimensional understanding we need. This requires long-term vision, sustained funding across multiple political administrations, international cooperation because no space agency can do it all alone, and patience to recognize that real scientific understanding does not happen in news cycles, but in decades and generations of cumulative work. Which next discovery about Mars do you think will be most impactful? Finding signs of current life, bringing samples back to Earth, humans stepping on the surface, or something completely unexpected that we don't even know how to look for yet? I would be fascinated to hear your bets in the comments. The deeper lesson that Neil deGrasse Tyson wants us to take away from this discussion of Mars is not just about Mars specifically, but about the nature of scientific knowledge and the limits of human understanding in general. Science is often presented to the public as an enterprise that generates progressive certainty, that begins with ignorance and ends with complete knowledge, that moves inexorably from questions to answers. But reality is much more complex and interesting. Science reveals successive layers of complexity, each answer unfolding into deeper and more subtle questions, the known expanding but simultaneously also expanding the perimeter of the unknown, our awareness of ignorance growing proportionally with knowledge. Mars is a perfect exemplary case of this nature of science. 60 years ago, our ignorance about Mars was simple and comfortable. We didn't know much, but we thought we knew what we didn't know. We thought we just needed to fill in some details. Today, after 6 decades of intensive exploration, our ignorance is much more sophisticated, much more uncomfortable. We understand enough to realize how little we actually understand. We see the gaps and inconsistencies in our models. We recognize the biases and limitations of our sampling. This informed and conscious ignorance is actually a form of progress. It is an essential step on the path to genuine understanding. But culturally, we have difficulty celebrating it because it feels like an admission of failure. Tyson insists that we reject this perspective, embrace uncertainty as an inherent feature of the scientific frontier, communicate it honestly to the public rather than hide it behind false confidence, and use it as motivation for continued exploration rather than an excuse for giving up. The universe does not owe us comprehensibility. There is no guarantee that the cosmos will operate according to principles that human minds can easily understand, and some aspects of reality may remain fundamentally mysterious, not for lack of data, but for limitations of our conceptual apparatus. But this does not mean that the effort is futile. Each layer of understanding we achieve, even if it reveals more complexity underneath, has intrinsic and practical value. It allows us to make better predictions, design more effective technologies, formulate deeper questions. And there is also beauty and wonder in encountering a cosmos that does not yield easily to understanding, that continually challenges us, that remains mysterious even after centuries of intensive scientific investigation. Mars, this red, cold world mere months away from Earth, This planet that humans have observed for thousands of years and studied scientifically for generations still holds deep secrets about its history, its present, and its future. There's something simultaneously humbling and inspiring about this, a reminder that the universe is so much bigger, so much richer, much more complex than any model we were able to build. When we eventually set foot on Mars as a species, when we establish a permanent presence on that alien world, when we perhaps even find native life flourishing deep underground, we will still be at the beginning of truly understanding that planet. And perhaps it is fitting that it should be so, that there will always be more to discover, always another level of mystery waiting beyond what we have already uncovered. If these reflections on the limits of knowledge and the eternal nature of scientific discovery resonate with you, share this video with someone who appreciates both mysteries and answers, who understands that the allure of science lies not just in what we discover, but in what remains to be discovered. There's a quote from one of the pioneering planetary scientists, Carl Sagan, Neil deGrasse Tyson's intellectual mentor, that perfectly captures the essence of this discussion about Mars and understanding, somewhere, something incredible is waiting to be discovered. Mars is literally there, visible to the naked eye several times a year when it's in opposition to Earth, a point of reddish light shining in the night sky, waiting patiently for thousands of years as generations of humans looked up and wondered about that alien world. And now we have rovers driving across its surface, probes continually orbiting, decades of data accumulated, and it still remains fundamentally mysterious in crucial ways. This is not a fault of science or scientists. It is testimony to the intrinsic complexity of planetary reality and an invitation to epistemic humility, to recognize that some mysteries do not yield quickly or easily, that authentic understanding requires patience, persistence, and a willingness to be surprised, confounded, and forced to reconsider fundamental assumptions again and again. Neil deGrasse Tyson turned this discussion about Mars into a broader meditation on how we do science in a universe that was not designed to be easily understandable, on the importance of communicating uncertainty honestly rather than pretending to knowledge we don't have, on balancing confidence in scientific methodology with humility about current limitations of our understanding. And that message is crucial now as we face decisions about huge investments in space exploration, as we plan missions that will cost billions and take decades to execute, as we contemplate sending humans to Mars, knowing that we cannot guarantee their absolute safety because we simply do not fully understand the environment. We must proceed, but we must proceed with open eyes about what we know and what we don't know, with respect for the immensity of our remaining ignorance, with a commitment to doing the fundamental scientific work necessary before taking irreversible steps. Mars will remain the most misunderstood planet, not because we have failed to study it sufficiently, but because each layer of study reveals more complexity, because it is genuinely an alien world that does not conform perfectly to our earthly categories, because nature is deeply subtle and does not give up its secrets easily or completely. And perhaps there is something appropriate and even beautiful in that. The first planet beyond Earth that we will directly explore as a species will remain a humbling reminder that the cosmos is larger than our understandings, that there will always be new mysteries beyond those we have already solved, that the journey of discovery has no definitive end, but only continually expanding horizons. When you look up at the night sky and see Mars glowing red among the stars, remember that that little point of light represents an entire world with a billion-year history, active geology we don't yet understand, perhaps even life hidden at depths we haven't yet reached, and certainly secrets that will take generations to unravel. This is the real Mars, not the Mars of science fiction or colonialist hype, but the scientific Mars, the planet that Neil deGrasse Tyson invites us to appreciate in all its bewildering complexity and inducing wonder. And if you've made it this far on this intellectual journey with me, thank you for your attention and curiosity. Subscribe to the channel if you haven't already. Leave a comment sharing which aspect of Mars you find most fascinating or confusing, and keep looking up. Keep asking questions. Keep exploring, because the universe is full of mysteries waiting for curious minds willing to face the immensity of the unknown with humility and determination. The red planet will continue to call us, challenge us, teach us that true understanding is an endless journey, and we may never fully understand it. But the attempt itself transforms us, expands our perspective, connects us with something greater than our individual lives, with the great cosmic story of which we are a part, and which Mars is also part of, a strange and wonderful alien world orbiting the same sun that illuminates our Earth, waiting patiently as we slowly, carefully, humbly learn to read the stories written in its red rocks and ancient dust.